It's time. The potential of data and AI is too big, and the problems we're solving are too important for it to be so hard. It's time to set your data up for success. Time to let it drive, because data is all grown up now, but we still haven't taken the training wheels off. It's time to be open, to unlock, unlimit, and unleash data. It's time to work together as data teams, as a data community. Innovation doesn't happen in isolation, because when we're united, we do what teams do best. Above all else, it's time to simplify. One place for all your data. One foundation for every workload, from BI to AI. One platform that runs where you run. One architecture that puts an end to the trade-offs and brings it all together. One Lakehouse. Databricks helps data teams innovate faster on the world's first and only Lakehouse in the cloud. Open, simple, collaborative. Now you can have it all your data, all your analytics and AI, all your data teams. One platform for today and in the future. It's time for Databricks.
Hi, my name is Leon Ella, and I'm a solution architect at Databricks. Today, we'll be talking about Databricks Lakehouse. I've got a couple of slides to go through to take you over the concepts of Databricks Lakehouse. And for the rest of the time, we'll dive straight into a Databricks workspace, and I will show you Databricks notebooks and some of the features of the product and some of the capabilities and the code that you can run inside of the notebooks. A little bit about Databricks as a company. We're a data and AI company. We've got over 7,000 customers worldwide, including Fortune 500 customers. We're the original creators of popular open source projects, such as Apache Spark, which you would have heard quite a bit about. Delta Lake itself has been open sourced. And of course, MLflow, which is used by data scientists to track their machine learning experiments, track the metrics of their models, package up their models, and then deploy them for inference workloads using model registry. Lakehouse is a simple platform to unify all of your data, analytics, and AI workloads. So how do we do that? So data Lakehouse platform sits on your existing data lake and can ingest all data, be it structured, semi-structured, or unstructured, batch or streaming, so whether it's batch or high velocity ingestion workloads, and it's unique in three ways. First off, it's simple. So we drive simplicity by eliminating silos that exist between personas and disparate tech stacks. Data only needs to exist once to support all of your data workloads on one common platform. There's no longer a need to move your data between a data lake and a data warehouse for different use cases. Your data can reside in a single source of truth in Delta Lake, and you can apply all of your workloads, all of your use cases to the same data set. The platform is open. It's based on open source and open standards to make it easy to work with existing tools and avoid proprietary formats. So data is stored on S3. It's stored in Parquet format, which is open source, and Delta Lake itself has been open sourced. The platform is collaborative, and specifically collaborative across your different data personas. There are a lot of different personas that need access to data to drive critical business outcomes. And with Lakehouse, the data engineers, analysts, and data scientists are able to work together to perform the workloads more easily. So data engineers, analysts, and data scientists access the same platform for all of their workloads. So whether you're looking to build pipelines to support batch ETL jobs, work with exploratory data analytics, run real-time data analytics, or even training machine learning models, Lakehouse makes all of this possible and allows for simplicity, openness, and collaboration. And this is why Databricks is a data and AI company. So let's explore this a little bit more. So here I've got 4 different organizations who use Databricks Lakehouse. So on the left, we've got a financial services organization. They were previously running Hadoop on-prem, and it cost them around $2 million a year to run. So they migrated to Databricks on AWS with an estimated cost saving of almost $1 million. Of course, beyond just the cost savings, they've gained a whole bunch of different capabilities that I will actually go over a little bit later to drive their business and get more insights from their customers and drive their business value. Next, we have a marketing service organization. So they were running various workloads, and it costs them roughly $65 to $70 per run. This is running their workloads with Hadoop on-prem, similar to the previous company. Databricks, of course, runs much faster. And at the same time, we don't just hand over the platform to our customers and hope for the best. We also have a bunch of experts working for Databricks that work with the customer to make sure that they get the best out of the platform. So as a result of collaborating with the customer, we're able to reduce costs to under $1 per run. Next, we have a retail company. So they enable the DevOps approach to data science and productionize machine learning models. So now the platform is used by every data science team in the organization, and they were able to gain annual cost savings of 15 million by using this unified data analytics platform. So the nice thing about Databricks is pretty much all of the features are available in the platform through APIs. So you're able to use those APIs and run a whole bunch of DevOps use cases with the platform. Next, we have a financial service organization again, and they establish statistically based fraud detection. This is basically a workload that was running in production for several years. So they extended that particular fraud detection pipeline. This is basically customers who are applying for credit cards through their phones. And one thing they wanted to be able to detect is whether it's actually a human being that's applying for a credit card or a bot. So they were able to apply various machine learning techniques, statistical techniques, to be able to detect where there are particular patterns that a user, a human being, would be using when they're entering data into a form. So they were able to detect what kind of pattern is being used and figure out whether it's a bot or a human being that was entering the data. And also they were able to use phone motion to be able to detect whether it's also a bot. So there are particular patterns with the phone motion as well to determine whether it's a bot that's applying for a credit card or a human being. So next, I'll dive into some of the architecture of Databricks Lakehouse. So here you can see pretty much the Databricks Lakehouse platform with the ecosystem of AWS around it. So you can see Databricks itself obviously is a platform that runs in AWS. The data that it processes resides on S3, so chips storage. We're able to integrate with also a bunch of other AWS services as well. So running Lakehouse doesn't mean you're isolated in a silo. You're able to integrate with a whole bunch of services in AWS. So if we start on the left-hand side here, we can ingest data using just S3, or if it's a streaming data, Kinesis, or even a managed Kafka service in AWS. We can also integrate with AWS Glue. So we also provide a meta store and a catalog available in Databricks control plane. But if you prefer to not use Databricks control plane and instead use AWS Glue, we can integrate with that as well. And of course, if you're doing model serving, so you can actually deploy your models to Amazon SageMaker. We can also integrate with ingest data from RDS or expose data to RDS, because we've got JDBC support for JDBC connectivity as well. And of course, we integrate with Amazon Redshift and Amazon Athena. So this can be done in a couple of ways. One would be you can have Amazon Redshift and Amazon Athena read Delta files directly by using manifest files, or of course, they can actually access JDBC interface in Databricks itself to pull the data out. So you can see we integrate with a whole bunch of different services in AWS within the whole AWS ecosystem. And as well as that, we can spin up workloads and compute using Spot instances, and we also integrate with Graviton as well to reduce the cost of your workloads. So that's all I've got in terms of slides. So I'll dive straight into the notebooks now. So all of these basically notebooks that I'm going to go through here, you will have access to them by downloading a package, and we'll share the link to that particular URL for you to download and import it in. So the way you import the notebooks in is you can go into the workspace and you can, basically for every user that accesses the workspace, there's a separate directory created, which is your home directory. And so you'll be able to just import that particular package. So either directly from a URL or from a file that you download, and it will actually create all the notebooks and you'll be able to just navigate through them just like I'm doing here. So I'm gonna, before I dive into the notebooks, I'm going to just demonstrate some of the features within the workspace. So here, as you have already seen, you can navigate between different notebooks within the workspace. And you can create subfolders as well into which you can place your notebooks. Now, we also have obviously ability to spin up compute. So I've already got a cluster running over here, but if I go to create a cluster, you'll be able to see the features to be able to create a compute cluster of your own. So you can give it a name. We've got different runtimes that you can run. So you've got the standard runtimes. If you're just running data engineering type workloads, you can just use a standard runtime. If you're running ML type workloads, then you can, of course, select a machine learning runtime. And we also, you can see here, support GPU-based workloads as well. So if you're doing machine learning training that can benefit from GPU, you can actually use GPU runtime and use GPU compute. So the machine learning, the difference between the machine learning runtime and the standard runtime is that the machine learning runtime has additional machine learning libraries that are pre-installed. You can, of course, install libraries yourself, and I'll show you that in a minute. But the machine learning runtime already comes with a whole bunch of pre-installed libraries, so you don't have to go doing that yourself. Some of the other things available here you can see is you can specify different instances that you can provision a cluster with. Now, most of the things here you don't generally need to touch, but a few things that are interesting here is this enable auto scaling feature. So you can see here, if I unselect enable auto scaling, I have to specify how many workers I want to run at any given time. If I select enable auto scaling, then I can actually configure the minimum and the maximum number of workers. So what that means is that if I'm running a particular workload, which is a heavier workload, and it would benefit from more cores, then the cluster can automatically scale to more workers to be able to run the workload faster. And once I'm running a smaller workload, it'll automatically scale down because the clusters are no longer being utilized, the nodes are no longer being utilized, and it will scale back down. So that's a nice kind of cost-saving feature that you have access to. The other interesting cost-saving feature here is ability to terminate your cluster after so many minutes of inactivity, which you can configure here. So what that means is that if you've got a particular cluster and you've got a bunch of notebooks being used using this cluster that are attached to this cluster, if somebody's gone home, let's say at the end of the day, at the end of the business day, and no one's actually using this cluster anymore, it will automatically shut down after a specified configured minutes of inactivity. Now, some of the other interesting things here that are another cost-saving feature is ability to specify spot instances for your cluster. So you can configure how many nodes in a cluster should be using spot. And of course, it's a great way to also save costs on your workloads. What that also means, of course, is that the node may be terminated and acquired back by AWS. But of course, the nature of the cluster is such that it's able to recover even though a particular worker may not be available anymore. You can, of course, specify that if a worker is not available and you want to maintain the particular number of nodes in the cluster, it can fall back to on-demand instances as well. Some of the other things here are, of course, ability to select an instance profile to run. So what that allows you to do is configure a role in IAM, in AWS IAM, and then have the cluster running with that particular instance profile, with that particular policy. And so that gives this cluster access to certain things like certain S3 buckets or any other kind of services available from AWS. And that would be another way you can actually configure access to Glue. So you can configure a particular role with a particular policy with access to Glue catalog. And then when you're running that particular instance profile on the cluster, it'll then have access to Glue catalog if that's the way you want to configure it. Of course, you don't necessarily need to do that with Databricks because the Hive Metastore will automatically be running in the control plane and available from there. Now, some of the other things here is you've got the ability to create a job. So the difference between a cluster and a job is that you can schedule a job to run at a particular time. So if you've got data that needs to be ingested, for example, let's say overnight, you can configure the cluster, the job to start up. You can configure the cluster that should be running as part of that job and specify the notebook or packages, jar files or wheel files, Python wheel files that need to run as part of the job. It will actually create a cluster, run that workload. Once it's finished running, it'll shut back down again. And so this is a nice way for you to create automated pipelines. Okay, we also have things here like repos, which allow you to also integrate with Git repositories. So you don't necessarily need to just have your notebooks maintained only in Databricks Workspace. You can attach your notebooks directly to Git repos and have version control maintained of your notebooks maintained inside Git repo. So let me go to the first notebook here. So what we're going to be doing today is I'll go through some of these things. So we're not necessarily going to be creating databases in Glue. We actually have a lot of information on Databricks website about how you can integrate with Glue, and basically it consists of creating a role, like I said before, with access to Glue, and then using that particular instance profile on the Databricks cluster. And then there's just one line configuration to say, yep, you want to be using Glue catalog for Hive Metastore instead of the built-in Hive Metastore. So we'll go through some of the data ingestion concepts, and I'll also show you the Databricks SQL product through which you can do BI dashboarding and some of the BI use cases. And then we'll, if we have time, we'll go into some of the advanced features as well, and I'll show you some of the interesting things that are available and coming up on the roadmap for Databricks. So when we talk about Lakehouse, of course, it's a combination of data lake concept as well as data warehouse concept that I talked about before. So you can pretty much use the same single source of truth. You don't need to move your data between a data lake for your, let's say, ML and AI use cases into data warehouse when you want to do some BI dashboarding. Delta Lake, which is the Delta Lake and the Delta Engine, which underpins all of these use cases of Lakehouse, is what allows you to have to be able to run your data warehousing as well as data lake use cases all from a single platform, single source of truth, and do that at scale with good performance as well. So I've already talked through the concepts here in relation to the fact that Databricks Lakehouse platform is simple, open, and collaborative. So we'll go straight into some of the code. So you'll notice here there are links to the notebooks that you can navigate to. Now, when you actually download the package yourself and run it, these links actually point to the current location for the notebooks. So if you actually import them into your home directory, they may not actually, you may not be able to navigate from the link, but however, you can navigate between different notebooks by just selecting, by going to the workspace view and just selecting the notebooks directly from here. And of course, there's plenty of documentation available on the Databricks website. And there are some links here to a whole bunch of this documentation. And we, of course, encourage you to go and have a look at the docs yourself and explore that. So let's go to the first notebook. So basically, in the notebook, you have support for Scala, Python, R, and SQL languages. So you can see here at the top, Python is the default language that I created this notebook with. However, if you want to switch languages on the fly, you can use this, this kind of magic command, as you can see here. And this allows you to select, in this case, I'm selecting SQL. You can also select Scala. You can select, of course, Python or R. So we'll go back to SQL here. So you can see here, the first thing that this notebook does is it does a bit of cleanup. So it removes the directory into which it's going to copy the data. It will then go and create a directory again. And we also have this magic command for the file system. So you can either run dbutils directly, dbutils.fs directly like that, or you can run %fs magic. And that actually does similar things to what dbutils fs will do. So for example, CP can also be run with dbutils. So I have to say Python here, of course. Actually, I already got Python as default. FS, CP, and then I could achieve the same result by specifying the directories for the source and for the target of my copy. And of course, if I want it to be recursive, I can say true. So %fs magic is effectively a way to run dbutils fs commands without actually using dbutils directly. Okay, so here what I'm doing is Databricks, when you install, when you deploy a Databricks workspace, it comes with some Databricks data sets. And here what I'm doing is I'm just copying some of those samples out to my AWS Lakehouse Dev Days directory. So now I've got my data. So one of them will be Parquet files, the other one is JSON files. So I've got my data sitting in my directory. But what I also want to be able to do is I want to be able to access that data as tables as well. So here I'm running my SQL commands. I'm going to drop my database, AWS Lakehouse Dev Day, and then create it again. So that, again, a bit of cleanup. And then this is just basically listing the files that I've copied to make sure that they have been copied, and also the IIT files. So you can see the IIT files are JSON files, and then these files here I'm going to be using for some sentiment analysis. So that's as far as preparation and cleanup is concerned. So now we'll go to the second notebook. And here things get a little bit more interesting. So with Databricks, as I was mentioning before, you can ingest your data directly from cloud storage, from S3, or you can ingest it from a streaming broker. So this could be Kinesis or managed Kafka, or you can ingest it directly from another relational database. So if you want to ingest it from a relational database directly, we have a JDBC connector, and you can use a JDBC connector to just run queries directly and bring the data back as data frames and store that. So what we want to be doing is we want to be ingesting data as raw data initially, and then we might push it through into a refined layer. So now we're going to be doing perhaps some data merges, some data cleansing, and then finally we want to expose that as maybe business level aggregates, so pre-aggregated data that we can actually query directly from our BI dashboards. So once I've copied the data across, so if my data is already in Parquet format, what I can do is I can just convert it directly to Delta format, right? So because Delta itself stores data in Parquet format, there's actually no need to undergo some complicated conversion process. I can just run a convert to Delta command over my Parquet files. And what that's going to do is it's going to create a transaction log file. There's a separate Delta log subdirectory that will be created, which will manage my transaction log. And just by running this command, that's all that I need to do to end up with a Delta file. So you can see here, I've run convert to Delta, and then I'm just running a query, select star from Delta to get some results back. And now it's in Delta format. Another way I can do it, if I don't really want to modify the source of the data. So by running a convert, I'm now changing my Parquet format to Delta format. If I want to leave my data in Parquet format, what I can also do is I can run copy into Delta command. So what that will do is it will copy the data into a separate location. You can see here that I specified from my source location, and I'll have to specify what the original format of the data is. And again, this will create a separate location for my Delta files, Delta table that I can query as Delta, but the original Parquet files remain unchanged. So the third way I can do it is I can just run this create table command. And what I'm doing is I'm creating a table and I'm saying the format for the table is Delta as select star from JSON. So I can pretty much read my JSON source files and then create a table in Delta format. So it'll have the same schema as the JSON files here. I can then pretty much move the data out of JSON format into my Delta format and have my table, in this case, because I'm not specifying a location for my Delta table, it will be what's called a managed table. So it'll be maintained inside Databricks DBFS location that's pre-configured. And this table will be managed. So what that means is that it's an external table. So if I actually go and delete that table, all of its data will also be deleted, but it's stored in Delta format. So again, you can see I'm doing a select from my table after I've created it, and you can see the Delta output coming out. Right. So this diagram here shows what happens when you ingest data with autoloader. So autoloader is a feature that's built into Databricks itself. So what that allows you to do is it allows you to ingest data as a streaming pipeline directly from S3 location as well. So you could have a scenario where you've got data coming into S3 on an ongoing basis. So let's say you're doing extracts from some relational database, or data is coming in from IoT devices, and those extracts are landing in some S3 location on an ongoing basis. So what happens is you want to be able to ingest that data into Delta as soon as they land. So you can then use autoloader. So what autoloader does is it will monitor the location for where the files are landing, and then as soon as the file arrives, it will then pick it up and you'll be able to ingest it into Delta using a streaming pipeline. So autoloader has two different modes of operation. One is where it'll constantly do file listing over S3. And if it detects that a new file has arrived, it'll ingest that file. Or you can automatically configure, and again, autoloader will do that for you, automatically configure SNS and SQS to monitor S3, and whenever an event is triggered that a file has arrived on S3, it will actually notify autoloader that a particular file has arrived through the message queue, and it will then go and ingest that particular file. That's two modes in which you can configure it. So, if you're worried about perhaps listing API calls that may be happening too often and the costs may be more than what you'd like, then you can configure the notification service to reduce your listing costs over S3 API as well. So what does that look like? So this is kind of another way of being able to ingest data besides the three ways I showed before. And this is more useful for constantly arriving data or constantly arriving files that you want to be able to ingest. So you can see here, the first thing we need to do is we need to specify the schema for the arriving data. And you can do it in two different ways. So the way it's done here is using the Python API, but you can also specify DDL for your schema as well, which might be a bit simpler because that can be specified as a string format. And you can see here, all I basically have to do is I have to run spark.readStream. So again, it's a streaming pipeline that's going to be running. My format is cloud files. I specify cloud files format as JSON. So I know this is a JSON data that's coming in. I'll specify the schema and then where the data is actually arriving, right? So this is the location that will be monitored for arriving files. And then to be able to actually store them, I'm taking this data frame that I returned from spark.readStream, and I call write stream. Now I'm storing my data in Delta format. And the mode in which I'm storing the data is append, so that data will be continuously appended into Delta. I've specified a checkpoint location. Now, what the checkpoint location is it's a location where autoloader will keep track of files that it has already ingested versus files which it hasn't already ingested. So even if you had a job running, you stop and start the job, because it's maintaining this checkpoint, which is persisted on S3 storage, it will know that in the checkpoint, here are the files it's already ingested. Don't bother ingesting the files that have already been ingested. And if you see any new files that have arrived, which are not in the checkpoint, ingest those. I'm also specifying here a trigger. So a trigger will allow me to specify how often do I want the files to be ingested. So for example, I could not specify a trigger, which means the files will be ingested as soon as they arrive, immediately ingested into Delta, or I can say a trigger should be running every 10 minutes. So if within those 10 minutes, a whole bunch of files arrive, they will all be ingested at once, instead of detecting every single file that's landing and ingesting it one by one. So I have control over that. And I can also specify trigger once, which means that if I've got a whole bunch of files that have arrived and I want to be able to run a job, ingest all of them and then shut down again, perhaps I don't want my pipeline to be running all the time, monitoring my location. I just want it to be run once if any files have arrived. And I can specify trigger once, and then the files will be, when the job runs, all the files that it hasn't seen before will all be ingested, and then the stream will actually shut down automatically. So that's a nice way for me to be able to perform data ingestion. So I've got multiple different ways in which I can ingest my data. And of course, autoloader simplifies the process for doing that. And I can specify through using option, I can specify for autoloader. So the default is it will do file listing, or I can specify an option where it will be based on notifications, and it will then create the SNS and SKS infrastructure automatically behind the scenes for me to be able to perform my ingestion. So one of the other things that Delta supports is it supports both schema enforcement and schema evolution. So by default, if I don't provide any configuration, then the schema will automatically be enforced. So what that means is that if I specify the schema for my Delta table, Delta file up front, any new data that's being ingested, if it doesn't conform to that schema, if I've got, let's say, a new column that's arriving, that ingestion will be rejected, right? So that's called schema enforcement. So what that means is that if I don't expect, I want to make sure that the data that's arriving conforms to certain schema. If there are other things in the new file that I don't expect, I want those to be rejected. Now, the other way I can do it is I can use schema evolution. So I can set my configuration here, auto merge enabled here to true. So I'm doing that right here. So I don't have to say auto merge enabled equals false, because that's the default scenario. And you can see here with that auto merge enabled equals false, if I then ingest, if I attempt to write something to my Delta table that doesn't conform to the schema, I will actually get a schema mismatch exception, right? If I then set it to true, then when I perform my write, you can see there is no errors. So the actual data was ingested, and I ended up with a new column. So my new column here. So I've got a data frame that I created with some additional columns which were not in the original Delta table, and so all of those columns will be available once the data has actually been ingested. So normally, if you set this configuration schema auto merge enabled equals true in your notebook, it will only be enabled just for your notebook, just for your session. And that means that someone else who's running a different notebook, perhaps even on the same cluster, for them, that setting will not be turned on. If you ever want to be able to turn on that setting for the whole cluster, then you can actually configure this on under Spark configurations for the cluster. So you would do that by specifying this configuration on the cluster. So if I go to the cluster and I do edit, then under my Spark configuration, I can say enable true. And if I restart the cluster now, then by default, auto merge will be enabled. So schema evolution will be enabled for me. Okay. So that's as far as data ingestion is concerned. So you saw that I was able to convert the Parquet files into Delta directly in place. I was able to ingest Parquet files using copy into command or ingest any other format, whether it's CSV or JSON. In this case, we did JSON by just doing a create table or using autoloader for kind of ingestion of data that's continuously arriving. So the next step is, so we've now ingested data into our raw layer. So in Databricks terminology, we call this the medallion pattern. So it's called the medallion pattern because the raw ingested data is silver, and then the refined is, the raw ingested data is bronze, and then the refined is silver. And then for the aggregates, that's our gold layer. So at the moment we've ingested data into our bronze, so our raw ingested data. So the next thing we might want to do is our bronze, our raw ingested layer is append-only data, right? So now we want to be able to bring that data into our silver layer, and we want to be able to actually merge our data into the existing silver table, right? So normally if you're dealing with Parquet, you'd have to follow a whole bunch of different steps that are outlined here, right? So you need to kind of identify the rows to be inserted, and then figure out which rows should be replaced, and then pretty much create a new temporary table, with a whole bunch of data combination of insert and update statements, and then delete the original table, and then rename the temp table back to original table. So there's quite a lot of steps, and this could be quite error prone. What you can do with Delta, though, is you don't have to follow that pattern. Delta supports a merge command. So what you can do with the merge command is you can match the rows by some primary key. And then for any row that matches, you can update it. And for any row that doesn't match, you can insert. And of course, if you have additional information that deletes, you can also delete rows. So this is what that looks like. So here you can see, so we've created our IoT devices silver table. So that's our silver layer. We're only using the 2 columns in this table. So the way you would actually perform a merge is you run a merge into command. So merge into IoT devices silver using IoT events bronze on device name in bronze equals device name in silver. So basically for any row that matches, so our device name in this case is our primary key. Of course, this could be more than one column as a primary key, in which case you would have an expression that says device name and some other column and some other column equals the column on the right-hand side. So when they do match, then we can say then update, and we set the column that is not our primary key to the incoming column. And then when not matched, then we perform an insert, and this insert will create a new row for us. Now, if we also had additional information about delete, so if we had, let's say, a change data capture stream coming in, and we had a flag in our change data capture stream that says this row has been deleted, and here's its primary key, then we could actually have a condition that says when matched and the flag, a particular flag is delete, then delete the row instead of doing an update on it, right? So you could perform deletes as well. So after running this step, when we actually run our query, we can see that the data, and when you run this yourself, you'll see that there are data changes coming in as well from our bronze. Now, the other feature in Delta that's quite interesting is this optimize command. So normally, and especially when you're ingesting that data from a stream, you could have small micro batches of data arriving. And normally, if you're dealing, let's say, with a Parquet format, as you persist the data, you're calling write stream to persist your data to S3, you could end up with lots and lots of small files. Now, if you have lots of small files, what happens is when you're running a query over those small files, the query doesn't perform because it has to process metadata for lots and lots of small files before the query is able to even run. So with optimize command, what you can do is you can compactify or compact those small files into a larger file. So that will pretty much create a new transaction in the Delta log. So you'll have the old small files still there because Delta itself is immutable, and you'll have a new transaction, a new version of the data set with compactified files, which is what optimize will do. And they're compacted to a particular configurable size. So what then happens is after the files are compacted, if you're running a query, there's a small number of files now, and your query can perform much more efficiently because it doesn't need to read metadata for lots of small files. Now, the other thing that you can do is you can run this Z order by command. So what Delta actually does is it maintains statistics inside the Delta log file, and you can see it looks something like that. So for each of the Parquet files in the Delta log, it'll maintain a mean and max, which are statistics for the a number of different columns. So normally, when the data arrives, it could be shuffled in some random order. So even though you may maintain mean and max, it won't be helpful when you're running a query with a filter, because your mean and max could be spread, your rows are spread across a whole bunch of different Parquet files. And so each of those files needs to be scanned to determine a particular row exists in that file. So what you can do is you can use this Z order command, and it uses an advanced algorithm to be able to lay out the files in a particular order in each of the Parquet files. So obviously, if it's just a single column, it's just effectively it's a sort. But if it's multiple columns, then it'll actually lay it out in a particular order. So it's a multi-dimensional ordering algorithm that it uses to lay it out in such a way such that when you're actually trying to filter by a particular column, the minimum number of files are traversed to be able to find that particular row. So because statistics are then maintained, so if you can imagine, if you're maintaining statistics about device name and they're ordered, and you then want to filter by a particular row in the Parquet in your table, and you've got, let's say, 10 Parquet files, because you've got statistics and you're filtering by a particular device name, it can then look at the statistics and determine that because you've got mean and max, that particular value can only exist in one Parquet file. So it will then only need to look in a single Parquet file and ignore and not bother looking in the other Parquet files, because it knows that that value won't exist there. So optimize Z order by is a kind of indexing, it's a kind of clustered index that you can have in your Delta files, which makes your queries run order of magnitude faster than what would otherwise happen. Now, you can see here also some of the other things that you can do with Delta tables. So here we are running a describe history command. So I talked about every time you perform a transaction, different versions being created in Delta log. So what describe history does, it actually looks through the Delta log and outputs some information about each of the different versions that were created. So every time you run you perform an operation over the Delta table, a separate transaction will be created. So basically, if you're ingesting a whole bunch of data, so if you're ingesting, let's say, 1,000 rows of data, either all of those 1,000 rows will be ingested, or if something goes wrong, you won't be in a situation where only half of those 1,000 rows got ingested. So you're now in some undefined format. So the actual ingest is transactional. So what that means also is that if you're actually running queries on the other side over the Delta file, you will only see those 1,000 rows once all 1,000 have been successfully ingested into a Delta table. So you've got a snapshot isolation when you're running queries. And so the way Delta is able to achieve that is by maintaining this transaction log, Delta log file, which is what describe history basically returns for you. And for each of the different transactions, it creates a separate version within the Delta log file. And it also records which operation was performed to create this particular version. So this is this concept of time travel that Delta has. So as a result of that, because it maintains multiple versions, what you can do is once you've ingested the data, you can then go and have a look, what did it actually look like at a particular version back in time, right? So we've got basically version 2, which is the latest version you can see here in history. What we can do is we can run a query and then determine what that looked like as of version 1. So prior to running this optimize command, for example, that you can see here. So we can also run this describe detail, which has additional information about the actual table you can see here. And so there's a lot more information about the number of partitions, the size of the files, etc., when they were created, etc., etc. Now, you can see here from time travel perspective, you can go back to a particular version of the data back in time. If you don't know which particular version you're interested in, you can also use this timestamp as of command as well. So this will actually figure out the particular version to return of the data at that particular point in time. So rather than just using as of version as of command to go back to a particular version, you can just, given that it maintains when that particular version was updated, you can then go back in time using this timestamp as of and return back the data set as it was back in time. So I mentioned this snapshot isolation when doing queries as well. So you can see here, if, for example, you're ingesting data using streaming and the data is coming in all the time, so you've got lots of transactions being committed as the data is arriving. On the other side, when you're running a query, your query obviously doesn't break, right? And your query has full snapshot isolation. So what that means is that as the data is coming in, if it hasn't been committed yet, your query will not see it. But the next time you run the query, it will see the latest version of your data set, unless you specify version as of. So it's quite nice because you can pretty much have your streaming pipeline ingesting data all the time. You can have compactification of your data, which means that even if you have small size events arriving, they will be compactified to larger files. And as you're running a query on the other side and you're querying this data, at any point in time, you will be able to see the latest version without you having to worry about, deleting temporary directories, swapping tables around, etc., etc. You can also, by the way, with this optimize, you can also turn on auto optimize feature. So what that means is that as this data is arriving as a stream, rather than you having to explicitly run optimize command to compactify the files, you can turn on this optimize feature and it will then compactify the files on the fly as the data is arriving. Okay, so now we've basically ingested our data into our Silver, so our refined layer. So now we can do things like we can use the data that's arrived to generate a whole bunch of features or create a whole bunch of features and use it for our machine learning pipeline. We can also then create our gold layer and generate a whole bunch of aggregates that we can then use for querying purposes. So you can see here that what this is demonstrating is we've gone from our refined, which is our silver, into our gold, which is our aggregates, and then we can do BI reporting on that. So again, what we're doing here is we are saying create a gold table now using Delta format again, and we are selecting some columns. Normally you would do that from silver, not from bronze. And then here you can do your aggregates. This pretty much aggregates data by multiple different levels. So we've run our aggregate command. So now we're going to run our optimize, and our optimize will actually compact NZ order by battery level. So now, after we've done our Z order by battery level, we can actually query our counts directly from our gold table. And by specifying this filter where battery level equals 0, it means that it only needs to look in a Parquet file where battery level 0 will exist. It won't look in any other Parquet files, which means that we will get a magnitude better performance running the query compared to if we didn't run our optimize command. So we can obviously run our queries directly from Databricks notebooks, but we also now have a Databricks SQL product. And Databricks SQL has a new Photon engine built into it. And the Photon engine is the new C++ vectorized engine that is magnitude faster than standard vanilla Spark. Now it's completely API compatible with Spark, so you can take all of your Spark workloads and run them on Photon and have much better performance. So Photon is actually built into the Databricks SQL, so you can run your BI queries from Databricks SQL and get better performance as a result. You can also run Photon on standard classes as well if you choose to do that. Now with Databricks SQL, so we actually, and I'll go into that in a minute. We actually have some visualizations built into Databricks SQL. So if all you're interested is in SQL features and you're not interested in Python, Scala, R, then you can just use Databricks SQL product. But we also expose endpoints from Databricks SQL, and you can pretty much attach a whole bunch of popular BI tools directly to Databricks SQL and have your BI dashboards served directly out of that product, right? So you can see here, whether it's Tableau, Looker, Click, Power BI, a whole bunch of different products. A whole bunch of them actually have connectors built in, or you can just connect to Databricks SQL using standard JDBC or DBC interface. When it comes to machine learning, you can see here, so what this code is actually doing is it's creating a Spark UDF. And so the Spark UDF, it's actually using a library to do sentiment analysis on the data, right? So I can pretty much configure my my UDF here, configure a library that I want to use as part of my UDF. And once I've done that, I can just run a standard query. So you can see here, it's just a standard SQL query. I've registered my analyze sentiment UDF, and I can pass into it my review column and get my sentiment analysis directly by using this package, get sentiment analysis directly coming out in my data set, which I can then pretty much query for, as you can see here, either through Databricks Notebook, and get my analysis out of that. So of course, there's quite a bit more to machine learning itself. So we've got products like Autoloader, we've got feature store in the product as well. So you can pretty much create your features, make them available through the feature store for multiple machine learning projects. We have Autoloader, which allows you to automatically build machine learning models based on the features that you plug into it. So these are some of the things that are available in the product to make your machine learning pipeline as easy as possible to use. And of course, MLflow is built into Databricks as well, and I talked about MLflow before as an open source project. So MLflow is built in, and you can just use MLflow experiment tracking features directly in Databricks without having to install anything. So it's a managed environment for you, and then use the machine MLflow model registry to deploy your machine learning models into the model registry, apply some MLOps governance to it. So you have your machine learning model go from development to testing or staging phase to production phase, and at each step, being able to do model approvals, notifications about as the models is transitioning, do model testing, etc., and then have that model available for production workloads. I'll talk a little bit about some of the advanced features as well. So one of the things we have available in the product, and you might have heard about it, is Delta sharing feature. So with Delta sharing feature, what you can do is you can just create a share of your data assets and make that share available to any third party. Now, Delta sharing itself has been open sourced. Because it's been open sourced, you can pretty much have any product have ability to connect to the Delta share. So you don't have to have Databricks on the other side if you want to be able to make it data available as shared data to any third party. And you can just create a share using the simple commands: create share, create recipients. Once you create a recipient, they will get notification and they will get a token sent to them by email, and then you can give them access. You can specify what sort of access they have through the share. And then you can then have a recipient be able to actually run a query directly over the data that you've shared with them. All that's required is a Delta sharing server. Now, this Delta sharing server is available in Databricks directly, so there's nothing for you to manage or install, and you can just share your data with third parties. The other interesting feature for data ingestion purposes, specifically building data pipelines, is we have a Delta Live tables, and with Delta Live tables, you can specify additional expectations that allow you to test the data that's coming in, and if it doesn't meet expectations, specify whether you want to fail the job, drop the row out of the ingested data set, or quarantine it out. And it's a nice way to actually build pipelines. You can see here, I can build my streaming pipeline directly in SQL. I don't have to use Python, and it's a lot simpler because here I just use create table command. I don't have to specify read stream, write stream commands. It'll automatically do it for me. And the other nice thing about it is that it will actually keep track and keep metrics about the data that's arriving. And so if for every expectation that is not met, it will maintain statistics, and I'll be able to then visualize that. I have access to see the whole pipeline, as you can see here, in terms of dependencies between different steps in my pipeline. The Delta Live tables automatically figures out what the dependencies are between the different steps in your pipeline, and also maintains statistics about the quality of the data that's being ingested. And the other thing that you can do with Delta is you can clone your Delta table, either deep or shallow clone. What that allows you to do is that allows you to, if you do a shallow clone, it will just make a copy of the Delta log, a transaction log in a different location, and you're able to then access the data in this different location, and it'll just point back to the original Delta files. And so you pretty much create a kind of a snapshot of the data at a particular point in time without actually having to copy. And of course, the deep clone will also copy the Parquet files as well, together with the transaction log, so you can have a complete copy of the data created for you as well. Quickly going into Databricks SQL product. So this is what Databricks SQL looks like. So what I can do here is I can create a SQL endpoint. And here it is, one I've created before. So here, when I create a SQL endpoint, I don't actually have to specify clusters. All I need to do is I need to specify whether I want it small, extra small, medium, large, etc. And I can also specify if I wanted to stop after a certain period of inactivity. And also, Databricks SQL has ability to scale to multiple clusters. So if my concurrency for the number of queries currently outstanding, the number of queries that users are sending at any point in time grows, then Databricks SQL can actually increase the number of clusters so that it can manage that level of concurrency as well. Some of the other things I can do here is I can turn on or turn off Photon. I can specify whether I want to use spot instances or not. And also, we have Databricks SQL now available in serverless form as well. So what that means is that Databricks SQL actually uses compute that's inside Databricks control plane, and the difference between running it inside your own control plane, your own data plane versus Databricks control plane is if Databricks SQL needs to spin up an additional cluster, there's generally a wait time to provision a cluster from AWS, could be up to 2 minutes. With serverless Databricks SQL, because we take advantage of economies of scale there, if you need to spin up additional compute to take care of your concurrency needs, the wait time is around 5 seconds, right? It's constantly getting smaller and smaller as our engineering team is working on reducing the startup time of serverless Databricks SQL. So the nice thing about it is that, first of all, the costs, both for AWS compute as well as Databricks, are rolled into a single cost. And also the fact that you don't have to wait up to 2 minutes for a new cluster to be spun up. It could be created within 5 seconds. So this is how you create basically a SQL endpoint, and with a SQL endpoint, you can then expose that and make that available for your BI dashboarding needs. So you can see here, it gives you JDBC URL. So this is the actual JDBC endpoint that you need to configure in an external BI dashboard or any tool that wants to connect via JDBC and run a query. And that's all that's required to be able to connect to the Databricks SQL product. And you can see here, we actually have built-in links to be able to go and configure connectivity from these tools directly to Databricks SQL as well. We also have monitoring capabilities here, so you can monitor the queries that are currently running against Databricks SQL, and we also have query history, and through query history, you can actually see what queries users have been running on Databricks SQL. You can see here, you can also configure permissions, which is now also integrated with our Unity Catalog product, which is in private preview. Now, just quickly, I'll go and show you a query that you can create. So here I've got, I'm creating a query. So this is over a data set that gives me access to basically New York City taxi trips. And what I'm doing here is, for example, this query here, I'm interested to see how many trips have occurred in a particular hour of the day. So if I run this query, you can see I've got a visualization here that tells me that the most number of pickups have occurred, what's this, at 6 o'clock in the evening, which is interesting. And also a similar query where I am looking at particular zip codes and I want to be able to see which particular zip codes have the most number of taxi pickups. Now, the way you can do this, of course, is you create a query. Then once you run a query, you can then go and create a visualization. And within the visualization, I've got access to different types of visualization. I can specify my columns. This is exactly what I use to be able to create these visualizations here. Now, once you've created your visualizations, you can pretty much attach it to your dashboard. So you can go and create a dashboard. So I've created a dashboard before here, and you can see both of those tables, both of those visualizations have been attached to my dashboard. And the way I can do this is I can go and edit my dashboard and add additional visualizations from the queries I created in the past. And then I'm able to share these dashboards if I want to with other people as well through the share button here. Okay, that's all I've got for you today. Yes, if you've got any questions, you can just ask them in the chat, and you'll have access. You have access to a link through which you'll be able to download all these exercises, the workshop material, and basically run it in your own cluster. You can pretty much create your own workspace by going to Databricks trial URL, which we've made available as well. You can then create your own workspace and then import these notebooks into that workspace and be able to run them there. Thank you.